Hi, I'm Robert Bolaños, and in this video I'll be talking about how to measure the output impedance of a power supply. So the obvious question would be, why measure the output impedance of a power supply? Well, by measuring the output impedance, it tells you how well your converter is able to regulate with a dynamic load. And when I talk about a dynamic load, that means a changing load. Let's say if you have your power supply supplying several circuits and one of them turns on, then you're going to have an increase of current. And in that case, you need to know, well, how much is my voltage is going to sag. So if you know the impedance and if you measure it, then you can easily calculate what your delta will be. So let's say, for example, once you have your impedance, and I do want to add that you notice here I have the S. That's the S, which is the J omega J2 pi F, which means that it's over frequency. Okay, so the impedance is measured over frequency, which is important. Okay, so let's say you have a situation where your power supply goes from 50% to, let's say, 100% full load. Okay, then if you know your impedance, then you can calculate what your delta voltage will be. Okay, so in case you have a increase of current, then your voltage will sag and it'll look something like this. And then if your current goes down or decreases, then you're going to have a little spike that goes up across like this. Okay, so you look something like this. Now those peaks and valleys have to be within your specifications. In other words, you're going to have a max spec and you'll have a minimum spec. Okay, and you want to make sure that when you have this dynamic load where you have more current, less current, you want to be sure that you keep within your limits. Okay, in other words, you want to make sure that you're meeting your specification. Another reason to understand and know about the output impedance is that it's also the basis to another very important topic, which is power distribution network analysis. Now this has gained much more acceptance the last few years, and that's because the voltages have been dropping. Okay, the voltages have been going lower and lower. They're, I believe, maybe to 1.2 volts, and the currents have been going up, 50 amps to 100 amps, maybe even higher. Okay, and typically these are applications where you use FPGAs. Okay, so knowing how to measure the output impedance is very important, because not only do you need to measure the output impedance of your converter, now you have to measure the impedance all the way up to your FPGA. So between the FPGA and your output of your converter, you're going to have a distribution network, a PDN. So you're going to have the layout, the wires. You're going to have vias, probably multiple vias, and then you're going to have some coupling capacitors or bypass capacitors. And since you have vias and layout, that implies you're going to have some L's. And since you have caps, that's capacitance, so you'll end up with certain resonance frequencies that may give you a problem, and you need to be able to damp them. Okay, so this topic of PDN is very important, and there'll be a future video on that. Okay, so the next topic is what parameters affect the output impedance. And here are some general statements, okay? They're very general. So at low frequencies, and when I say low frequency, I'm talking about below 1 from 1 hertz on lower. And at those frequencies, the output impedance is determined by the gain of your op amp, which could be inside your PWM, your load, your divider, and your modulator, which typically would be your PWM. And then you have the mid frequencies, and the mid frequencies typically I would say would be from 1 hertz all the way to your crossover frequency. I'll put CFC for your crossover frequency, and that could be anywhere from maybe 1 kilohertz maybe up to 10 kilohertz. Okay, so basically it's wherever your loop response crosses over. That would be your crossover frequency. And then at the higher frequencies, that would be from where the crossover all the way to hundreds of megahertz. Okay, and those frequencies, they're going to be dominated by the capacitive load, the ESR, and then what at very high frequency in the hundreds, you're going to have the inductance of the components. So you're going to have the inductance, the parasitic inductance as your capacitive loads, and then there's some inductance associated with the layout and also with the VS. Okay, so those all turn into play, and I have a simulation that kind of shows that. Okay, so I'll be using the VRTS demo board from Pico Test. It's a simple regulator. It's a little series pass transistor. It's a Darlington tip 120, and then you have a feedback here. This is the R2 is the injection resistor, and then R3, R4 is the divider, and then the feedback goes to the TL431, and then C1 and R5 is the compensation. So this is the feedback loop. And on the board there's a little switch where you can switch capacitors in and out and the load. I have the switch, this switch where I'm using a 100 microfarad tantalum, and I have this switch turned on where I have 130 ohm load resistor as my load. So this is the board that I'm using to measure the output impedance. Okay, so now before I measured it, let's get a little bit background. I have a deeper understanding of the output impedance. Here I have the board simulated, or I have a schematic. It's drawn a little bit different, but it's basically the same. And I want to show that here is the TP100, here's the resistor, here's my tantalum cap, and then I'm feeding back my divider, goes to the TL431. Here's my compensation. Okay, so basically here is the circuit that I will be simulating. And to measure the output impedance in SPICE, what you do is you do a AC analysis, you put a current, and you set the amplitude or the magnitude to 1, and that current will output here, and in this case, when it sees a resistor, that current will be multiplied by the resistance and develop a voltage. So the voltage at this node really represents a resistance or an impedance. Okay, so this is the way you simulate. Okay, so now this is the general equation to calculate the output impedance of any regulator. Okay, so here this is the closed impedance, and it is a function of the open loop impedance divided by 1 plus the total open loop impedance. Okay, so when I say open loop, what do I mean by that? Basically what you do is you can cut here, this is the feedback, and you start at this point and you get the transfer function of your divider, and then in this case of my PWM, or in this case there's a internal op amp inside the TL431, and then typically you would go through a PWM, but in this case we're going through a transistor, so the transfer function for this one I'm going to set as 3.3, which is the output, divided by the voltage that I measured here, which is 4.52. So that is the gain of this section. And in this case, I'm going to label it as PWM. So basically, that's the loop. Okay. So here you can see the transfer function of the divider. And then here, this is the measured gain of the internal loop. The internal op amp that's inside the TL431. It has a gain of 55, which turns out to be 562 volts per volt. That is the gain. And then here I set this gain as 3.3 divided by 4.52. That's the gain. And then at very low frequency, you can neglect the capacitor, the ESR, and the inductor, because at very low frequency this is basically an open. So basically with no feedback, the open loop impedance is really your load resistance. So here I make this statement: our load is equal to Z open loop at low frequency. So once I have everything defined, here's my total loop, divider, gain of the op amp, PWM, and the load, and that goes here. And here is the final equation with the number. So this calculates that I should read approximately 2.2 milliohms. Okay. So now here's the equation, 2.2 milliohms. And when I do a AC plot, this is the plot that I get. And here you can see at very low frequency, I measure 1.98 milliohms, which is pretty close to what I calculated. Okay, so this tells you that this is pretty close to what I've calculated. Okay, so now here is a plot of the same output impedance, and there's certain sections that you can read out, and if you learn how to read this, it makes it much easier to interpret what is what. So anytime you see a horizontal section, that's going to be a resistor. Okay, so in this case, this section is the DC impedance at very low frequency. Okay, so basically the converter looks like a 2 milliohm resistor at low frequency. Then at this section, anytime you have a a rising impedance, that is typical of a inductor, L. Okay, so this represents the effective inductance of the converter. So basically, the power supply looks like a L inductor. Okay, and then as you can see, the impedance goes up, and right at this point where it peaks out at the maximum, that is the crossover frequency of your loop. Okay, so that's something very useful to know, that if you do see a peak like this, the very first peak, that will be the crossover frequency of your loop. Then when you see a downward slope, that is typical of a capacitor. So in this case, this is the capacitance of my main capacitor. In this case, I'm using a 100 microfarad capacitor. And then after that, then you have another horizontal section. That's the ESR of the main cap. And then again, here you have another ascending plot. This is the parasitic and lead inductance of the cap. Okay, so just by looking at this plot or any other plot, once you know that if you have a ascending plot, it's an inductor, descending plot, a capacitor, anything that's horizontal is a resistor. Okay, so this is the main idea that I want you to get, that by looking at this, you should be able to interpret what is affecting what. Okay. Okay, so here I have another simulation. In this case, it's a little different, and what I did is I replaced the 431 with a discrete model. So basically, this is a TL 431 model equivalent. And the reason I did that is because this op-amp model, I'm able to program the gain. Okay, so here you can see that I programmed the gain to 562 volts per volt. Okay, so what I wanted to do was I wanted to sweep. I wanted to change the gain from gain of 10, which is 20 dB, all the way to 100 dB. Okay, so this would be a gain of 10, 100, 1K, 10K, and 1K. Okay, and here you can see that as your gain of the op-amp is increased, the impedance starts getting lower and lower and lower. So right here, this is approximately 1 milliohm, while here it's 100 microohms and so forth. So this is why I say that at very low frequency, the gain of the PWM that you're using is what will dominate at very low frequency. Okay, so this is the equipment that I used to measure the output impedance. I'm using the Picotest J21 11A line injector, and this injector is good if you're using uh, 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 to measure a voltage anywhere from 1 volt all the way to 42 volts. Okay, so if you have any voltage in between, you can measure the output impedance with the J2121A line injector. The other piece of equipment that you need a FRA. In this case, I am using the Omicron Labs Bode 100. I recently upgraded my lab by purchasing the Bode 100, and with these two pieces of equipment you can measure it, the output impedance. Now I do want to say is there is two other methods that you can use. You can use the one port method, and there's another one that's a little bit more accurate, which is the two-port shunt through method. Okay, now those are very accurate for low impedances. The only thing is that you want to be sure that your output voltage is lower, or basically either equal to 3.3 or lower than 3.3. Okay, so those two methods you can use, and you don't need to use the J2121, but anything above that, so you can say anything above 3.3 volts to 42 volts, then use the line injector. Anything below 3.3 or below, then you can use the one port or the two port measurement. Okay, here I have the configuration of how to hook up the Bode 100 and how to hook up the J2111A current injector. What I have here, I have the block diagram, and the reason I'm using the block diagram is to kind of explain what is happening inside the 2111A current injector. Okay, so we'll see how it works. So basically, we're going to connect a power supply to our power supply that we're going to measure, and the power supply will be connected to a load. In this case, I'm using 130 ohms. And what you want to do is you want to connect the output of your power supply that you're testing. You connect it to the J2111A. Okay. Then that same node, you want to connect channel 2. Channel 2 will be measuring a voltage. And it's going to be a delta voltage. Okay. And then here you have the output of the Bode 100. It's going to be outputting a signal. That signal goes through this summing amp, and it goes into a amplifier. That amplifier then drives this NPN transistor. That NPN transistor, then what it does is going to cause current to be drawn. And where does that current come from? That current actually comes from your power supply. Okay, so that current goes through the diode, through the transistor, and through this current sense. So it's going to develop a delta voltage across the resistor. The delta voltage is really a current. So then that goes through a low amplifier. So you're going to have a delta I coming out from the J2111A, and that is fed to channel 1. So channel 1 is going to have a delta I, and channel 2 is going to have a delta V. So to measure the impedance, you get the delta V and the delta I, and you got your measurement. Okay, so now that we know how to hook it up, let's measure the output impedance of a power supply. Okay, here we have the Bode 100, and I have it hooked up with the J2111A current injector. And what I'm going to do is I'm going to measure the output impedance of this test board. It's the VRTS demo board from Picotest. What it is essentially is a regulator, linear regulator. It has a series pass device here, and your output is across these two terminals. This is the negative, this is the positive. And what I'm doing is I'm connecting across the output. I'm connecting these two, the red and black connectors, and those go to the J2111A. So this is the output of the modulator, and then this, which is the IMON, this goes to channel 1 of the Bode 100. So this is measuring current, and then this channel 2 is your voltage measurement, and that would be this times 10x probe. So I'm connecting across the output, okay? And then this is your input, and right now I have this at about 10 volts. So the output is basically 3.3 volts at 100 milliamps. So this is the way we hook it up to measure the output impedance. So now we're ready. Ready to measure the output impedance. Okay, so we go to the Bode Analyzer Suite, and we go to the Impedance Analysis tab, and we select the voltage current, which is pictorially or schematically, this is what we're going to be doing. We're measuring the current and the voltage of the device under test. So we start the measurement. Okay. Now, before you start the measurement, you have to make sure that it's configured correctly. So you click on the impedance reflection hardware setup, and the probe, this is your current probe, channel 1. This has to be terminated at 50 ohms. Okay. And attenuation or the scale should be 1:1. And then the probe is a times 10 probe. So we select 10:1. Once we select that, then we should be fine. Okay, so now we're ready. So now let's go ahead and I'm going to measure from 10 hertz to 40 megahertz. And we press continuous. Okay, so we're going to go ahead and delete the phase measurement. Okay, so this is the output impedance. So we're going to up the current or the signal. So we're going to go to the maximum, which is 13. Okay, and then let's go with less attenuation. And that looks pretty good. Okay. And let's see what else we can do. Now, here is the bandwidth. If you wanted to scan a little bit at a faster rate, but you will have a noisier signal, provided that you don't have enough signal, input signal. Like for example, if you lower this, so you start getting some more noise in your system. So if you provide enough signal, you can get a much cleaner measurement. Let's go ahead and set it at maximum. Okay, so that's pretty good. Okay, so I'm going to go ahead and stop and just do one single sweep. And I'll go over. Okay, so here we have the single sweep. Okay, so now what we're going to do is we can use the cursor, and this little hump that you see right there, that peak, that is the crossover frequency of your bandwidth. So, and that bandwidth is 6.06 kilohertz. Okay, so that's very important. So another thing, another thing that you can do is you can do the NIST, which is a non-invasive measurement of your your regulator, and you can add, I believe, another add a second trace. Okay, but I want the trace at a different. I went the wrong way. Okay, you want the axis, one axis per chart. Okay, so we have that. So now what we're going to do is we're going to try and measure the phase margin. We already know what the crossover frequency is, or the bandwidth. So now for the measurement, we'll do a QTG. I believe that's the Q. So we'll do an optimize. Okay. And I can select this to be a little bit. Okay. So let's take another measurement. And I'm going to lower the bandwidth to see if I can clean this up a little bit, but we have enough information to measure the phase angle. So okay, and let's see if it cleans up a little bit more. If I go to 0 dB, cleaned up a little bit. And let me go 10. Okay, so what I want you to notice is this is the impedance, and this is the, I believe it's the Q. I'll just say that it's a QTG. And if you notice that the peak up here coincides also at the same peak. So we put that there. So now there's this function where you can go to the cursor, and then where it says none, basic phase margin calculation. You click that, take that off, and right here it calculates the phase margin of 36.75 degrees, which is a little bit on the low side, but this is a nice capability that you can measure the crossover frequency and the phase margin without actually having to tap into the Bode injection uh, method. So this is a method that you can use for let's say three terminal regulators that don't have a injection point. This would be one of the ways that you can verify the stability of your regulator. So anyway, this is the way it's done. If you have any questions, you can post your questions here or on my website or here at LinkedIn. Thank you for watching.